All right, good morning. Should have maybe just said we'll do everything from home today because it's Thanksgiving. A nice little campfire, fireplace. Okay. Last time we talked. Well, last time we had an exam, but before that we had talked a bit about redox chemistry. And I intended to just touch on the basics of some of the redox. I think you had a little more on the homework. I was worried at first that I had given you like the redox diagrams, and we definitely didn't get to that point. But my aim was, I think I talked with a couple of you, aim was to just touch the surface of redox stuff on the exam, kind of say some things are more or less oxidizing and kind of some of those properties. So apologize if that was a little unexpected what you had. We'll talk about that more later. I'm not going to go through the exams right now. Probably be the Thursday after Thanksgiving, so a week from Thursday we'll discuss the exams, I think. Have not graded them yet. Okay, so today we're going to finish up with redox chemistry. Take a look at some redox diagrams, both PE/pH and PC/PE. Kind of start picking back up where we left off last time. As for the rest of the semester, that leaves us with 2 lectures after Thanksgiving, one of which we'll probably talk at least a little bit about the exam. I probably won't spend a huge long time on it. And my plan is to talk about some aquatic photochemistry. That's my expertise. I'm very familiar with it, but I'm also going to bring in kind of what the book has to say and contextualize it within the wider, like how do we typically think about it for environmental engineering systems. So it should be a good mix of insights, not just my own research, but also sort of the book's perspective and what are the basic principles. So I hope to do that. I think those will be a little more interesting. And so as far as stuff that I know a lot more about. Redox chemistry has always been something for me that I feel like I'm close to it with the photochemistry. There's a lot of related processes, but I've never felt like, oh yeah, I know everything about that stuff. Okay, so with that, the only other thing to consider really is the kind of the MATLAB and project, or the. You can also choose the Mintech version of it if you're not comfortable with MATLAB and have not been feeling comfortable with that. Either way, my expectation is from here to the end of the semester, there's going to be some self-learning involved. That's always true for coding. That's going to be true with the Mintech thing. It's not coding, but it's, hey, how do we use this software thing? How do I get put the inputs that I need to get it to give me the equations, and perhaps combo that a little bit with Excel to produce figures, or even just to figure, to learn how to do this procedures. Of course, if you feel like some part of all that is just completely unreasonable or you're completely lost, I want to hear about that. I want to hear from you. So communicate with me about it. And I think there's a little room for you to explore and engage in that. So hopefully that's a good thing. And hopefully you don't have to think too hard about that over Thanksgiving either. All right. So we left off talking, last time we talked about redox, talking about the Nernst equation, relating the delta G to our standard reduction potential. So the E standard thing here, we refer to it as a standard reduction potential, and that's going to be the convention. You'll often hear people talk about oxidation potential or redox potential. Almost all of that is just shorthand or kind of a related way of talking about it. But the convention is to say reduction potential. So maybe other textbooks will say oxidation potential, and maybe that's just as good. So I'm just making the point that it's really all relevant to how you write your equation. Is it the reduction potential or is it the oxidation potential? Does it matter? It's going to convey the same thing when we put all the pieces together and use the math. So it's not a big deal. So we talked about this last time, how the standard reduction potential relates to a particular reduction potential just in the same way as the standard Gibbs free energy for a Gibbs free energy for some reaction. And we can convert between the two by dividing by negative n times the Faraday's constant, where n is going to be that stoichiometric coefficient. And so we can end up with this reduction potential is equal to the standard reduction potential minus RT divided by NF times the natural log of the activity of the reduced or the reduction reaction divided by the activity of the oxidation components, or the species that are reduced on top and the species that are oxidized on the bottom. Okay, so that's sort of some of the standard equations or relationships that we might need for solving for reduction potentials. All right. So we also talked briefly about, okay, the relationship here, we can derive it, and we can reformulate that into a log form that gets us in a way where we can relate to a log k, as we've seen, and really just dividing, so taking from a natural log to a log, that's the 2.303. And if we take 2.303 times R, which is the gas constant, times temperature at standard temperature, divide that by the Faraday constant, that all comes to one constant, 0.059. Okay, so we can lump all that together and simplify all this quite a bit and say E is equal to E naught plus that constant divided by N times log of the activity. All right, and one last thing we noticed is that convention for the delta G equation has a minus here, but since we are going to write this backwards, we're going to flip it by multiplying that by -1, meaning we get a plus here instead of a minus. And that's just literally because the convention for how we write the activity quotient there is backwards. Okay, so just a quick note on that. So that's basically where we left off. All right, so today I want to talk more about cell potentials as a way to look at redox systems. We looked at a lot of half reactions last time we talked, to the point where we could balance a half reaction and a cell. So the standard potential for a cell would be the combination of two reactions. Okay, and we call it a cell or an electrochemical cell just in the same way as when we talk about batteries, we might call it a D cell, or a battery that has X number of cells in it. What this is referring to, as we'll take a closer look in a moment, is the combination of two reactions put together that is in total a cell. Okay, so it's quite simple to say that the standard potential for a cell is equal to the standard potential for the first half plus the second half. Likewise, we can get it in a particular condition, so it doesn't have to be the standard potential. It could be E cell equals E1 plus E2. So let's take a quick look at copper and zinc in combination real quick. And here's where we'll see the order with which we're writing it is going to matter in terms of whether or not it's favorable. And that's also going to, like physically, that means are we reducing or oxidizing copper? One way we write it, we're oxidizing it. The other way, we're reducing it, right? So that will matter. It'll basically flip the negative sign or add a negative sign. Okay, so let's take a look. Copper 2 plus 2 electrons. So this is 1/2 reaction for the redox interactions of copper and zinc. So copper 2 plus 2 electrons will get us to copper. That's the first half. And the standard potential for that is 0.34 volts. That's something we could look up the reference. We could use our Nernst equation and find that. It's also something we could perhaps measure. So we're just going to say that's known, that's what it is. For the zinc reaction, the half reaction looks like this. Zinc 2 plus 2 electrons is in equilibrium with zinc 0 valent, and that has a standard reduction potential of negative 0.76 volts. Okay, so with those two just by themselves, we could just write those two half reactions, then think about, all right, how are we going to combine them, right? Instead of writing one up front with the E on the right side, our convention is to always start with we're going to add electrons to the left side essentially, almost always, because that's the one that's going to be, that's in the most oxidized state, going to be reduced onto the right. So since we write them both that way, we have to subtract one from the other. So we're going to subtract zinc. This part actually doesn't matter too much which one we subtract from the other, as we'll see. But we'll take it this way. So we're going to subtract here. So the zinc's going to move over to the right side. The 2 electrons would move to the right side. If we decide to just reverse it and add, however we want to look at it, we're going to end up with a net reaction of copper 2 plus zinc 0 valent is in equilibrium with copper 0 valent plus zinc 2 plus. And all we have to do now is take the 0.34 minus a negative 0.76, and we get 1.1. Now, if you think about it, we could flip this and say negative 0.76 minus 0.34 would give us a negative 1.1, right? But if we do that, we have just flipped the arrangement here. Okay, so that's the difference. So which element is going to be on the left side, right? That's going to depend on how we write up the reactions, how we set up the addition or subtraction, right? Okay, so when we have a positive standard potential, standard reduction potential, a positive E or E naught, that corresponds to a negative delta G. And that's coming back from what we were talking about a minute ago, where this equation is almost the same thing as where we had G is equal to the standard Gibbs free energy, and I guess this is delta, right? Minus all that stuff, right? So the relationship here is basically, it's almost a negative of the other. So it's not exactly, but we can kind of imagine it that way. So when the standard electrical potential or standard reduction potential is positive, the delta G is going to be negative. That means it's going to be spontaneous, likely favorable, right? So if we flip the reaction, the inverse will be true. So whereas for the copper 2 plus being reduced, thereby oxidizing zinc to the point where we have copper 0 valent and zinc in an oxidized form, zinc 2 plus, that one's favorable. But if we flip it so that we're taking copper and oxidizing copper and reducing zinc, that's harder to do. That's going to have a negative standard reduction potential and a positive delta G. So that's not going to be spontaneous. We would have to perhaps add energy to make that happen, or add some sort of input. Okay, does that make sense? All right, so that's kind of, as you might start feeling about that, that's a bit of a picture of a battery, where we can extract energy from this chemical reaction, or we could push energy into it if we're going to recharge it. And some systems are rechargeable. I'm not going to talk too much about that. I think I would need to invest a little more time researching battery technology a little more specifically, but we will look at these electrochemical cells for a few minutes here and it is a lot like a battery. Okay, so if we're taking some sort of experiment, we'll typically have a cell that's composed of two electrodes, an anode and a cathode, and these will typically be in a metallic, a zero valence state, and then reactions will occur at that surface with that species, converting one way or the other to oxidize or reduce species. And this will happen in the context of an electrolyte solution that has a salt bridge, we call it, that allows electrolytes to flow one way or the other, or really probably both ways depending on which electrolyte we're talking about. So we have a flow allowed for electrons and a flow allowed for the electrolytes, which are ions in solution, to allow for a net charge balance, right? Because if we're flowing electrons one direction with no salt bridge, it couldn't actually happen because we can't violate electroneutrality, right? So salt bridge, we'll just say keeps electroneutrality, because otherwise we just simply can't have more charge on one side or more positive charge than negative charge. It violates kind of the natural system. The only way around that would be to take or give electrons to something somewhere else. Maybe the beaker is touching something and that can transfer or something. Generally, that's pretty unlikely. Glass tends to be pretty insulating and not necessarily going to give enough electrons or take enough electrons to notice. Okay, so the electrodes we can describe, and first I'll say that the cell in total, the reduction potential for the cell would be equal to the reduction potential of the cathode minus that of the anode. And we can abbreviate that EC minus EA. So we can describe it then in those terms, say this minus that. And if we think back a moment, here, the first half and the second half, here we said plus, but if we flip it, we could do minus if we wanted to, or it could make some sense that way. We're going to call the anode the one where the oxidation half of the reaction is occurring, and the cathode where the reduction is occurring. Now, to me, that sometimes feels a slight bit counterintuitive, because we also probably recognize that anode is the negatively charged one, which reminds me of electrons, as if there's going to be lots of electrons around, which should mean, or like my intuition tells me, oh, that should be reducing. I'm going to come back to that in a second. Cathode, on the other hand, is our positive charge, or positive lead, and that's where the reduction half occurs. So the way I make sense of that is to consider that the electrode that is giving electrons versus taking electrons, that's how to think of the cathode and the anode. So the anode takes electrons, so it's oxidizing other things. That's why the oxidation half is occurring there. So that the electrode itself is taking the electrons, oxidizing something else, and because it took those electrons, now it has that negative charge. Okay, so that's the way it made sense to me. And in reverse, the cathode is achieving a positive charge because it's giving away electrons, reducing whatever's around it. Okay, so it's left with a positive charge. Now, is that completely technically correct? And do electrons really flow? There's some electrical engineering and physics, electromagnetism involved here that I'm not really going to get into, and there's maybe some debate about how all these things are actually moving or transferring, but that's kind of the deal, or a simple way to look at it. And so if you ever changed a car battery or jumped a car, you probably remember, okay, there's some order we have to do this, and we're supposed to do that and the other. And part of those protocols are to make sure that you are approaching it in a way where you are matching appropriately the two electrochemical cells in a way that's putting you at the least risk of accidentally zapping yourself, right? So it's positive to positive, and it's generally, I think the common practice is to go ahead and start with the cathodes or the positive charge, and you'd put one on the charged battery first, and then the dead battery, and then you do the negatives, just making sure you never short them, right? Okay, anyhow, so that's kind of the way to make sense of it. And so the combination of, for example, two beakers, each with an electrode in them, the salt bridge across, and an electron bridge, that's our cell. And that could also be a battery where this voltmeter here, or potentiometer, can measure the voltage, the potential across there. Now, if we allow that reaction to occur, then electrons will travel. And so when we have a voltage, which is kind of a voltage is like a potential energy. It's like lifting an object up, right? Now my water bottle has some more potential energy, right? And so if I drop it, there's energy exerted when I catch it, right? Or if I let it hit the ground, we'd hear it, and hopefully it wouldn't break, but it could break for all that energy, right? So voltage will be a similar concept where we can have high voltage, high potential here, but until something is flowing, it's not necessarily exerting that energy. So the voltage with the current is kind of that energy value. So as electrons are moving, that then is the energy we can extract potentially. Or in some cases, we could reverse that, put energy in, and restore or recharge the cell. Okay, so what's actually happening at these electrodes? Here we notice we have zinc over here and copper over here. We're going to have some dissolved copper 2+ here and dissolved zinc 2+ here, right? If we have some equilibrium with the solution. And the deal is we can then oxidize or reduce things accordingly, and that allows for both half reactions to proceed. Now, if we start with 1 molar of each of the species there, that kind of gives us a good starting point, and we can consider how much of a reaction can we ultimately achieve. So there's a couple questions there about how fast is it going to happen? So what are the kinetics? And when do we reach equilibrium? So for this particular example, we could consider, we already calculated our E as 1.1 for the standard, right? So this is our equation, E equals the standard potential, which we calculated or looked at already, plus the rest of this equation. This is the 2, that's for how many electrons are involved in that reaction, times log of copper over zinc in the 2+. And we will say that we find the equilibrium with the Nernst equation here when this is 0. I guess maybe I should draw it that way, right? So we can set that to 0 as the moment where we find an equilibrium. Just like delta G is 0, the change in Gibbs free energy is 0 when we reach equilibrium, we can say the same thing for this equation. So E becomes 0 when we reach equilibrium. That means we can solve for a ratio of copper to zinc in the 2+ form at equilibrium. And if we do that, we can say, we can take all this, add or subtract rather 1.1 from the other side, and then divide by this stuff, and then convert from the log. Ultimately, what we get is the copper divided by zinc, molar concentrations in these states, is 10 to the negative 37.28. So that is an exceptionally small number, right? So there is, when we reach equilibrium, the amount of copper is 37 orders of magnitude smaller than zinc, if I said that right. So effectively, if we started with 1 mole per liter of each and each side, we're going to reach equilibrium when copper is approximately 0, right? Maybe technically not 0, but that's 37 zeros before you reach the decimal place. That's pretty much 0. So our battery then is dead when copper reaches 0, and conversely, we've generated some more oxidized zinc. So all of the copper is going to the metallic form, C, like a 0 valent, and all of the zinc, or as much zinc as this cell can afford, so the electrode is going to have plenty of zinc, but the electrochemistry here is only going to provide enough electrons, or take enough electrons to get it to the point where we have 2 moles per liter, right? Because we're balancing the charge here. It's a chemical reaction that way, and so for every 1 mole or 1 molecule of copper, we can get 1 mole or 1 molecule of zinc to go the other way, right? That's the balanced redox combination of the balanced redox reaction, right? Back here we said if we're taking Cu2 plus 1 zinc, we can get 1 copper 0 valent and 1 zinc 2 plus. Okay, so overall that's still the same reaction. So that's where we get the 2 moles per liter for zinc 2 plus. Okay, does that make sense? So that's kind of the practicality of what's happening in our battery. Now we already mentioned the car battery. You've probably heard these called lead acid batteries. And so I don't remember all of the chemistry, but I think we've got a redox involved with lead, and the thing is kind of lined with lead, and then it contains acid. In that acid, we've got electrolytes, and then there's going to be a bridge across to the other electrode, so there's going to be 2 cells. Now, if you, anybody happen to remember the exact acid and electrodes? I think it might be sulfuric. I think that's battery acid. But you might also recognize or know, or maybe didn't know, but have been frustrated by, eventually these batteries will kind of go bad. They'll lose their ability to hold their charge, and theoretically they shouldn't if we could convert, go back and forth in these phases, no problem. Well, there is a bit of a problem if there's some loss of water. It actually turns out to be one of the major problems. So technically, you can preserve these batteries a lot longer and better if occasionally you maintenance it by adding some DI to the cell appropriately. And a lot of them do have a port for that. I've never quite bothered enough since knowing about it. I was like, well, I could grab some from the lab, I could try this and see what's up. But by the time the battery goes bad, it's a little too late. Because what happens is if you reduce the water from evaporation, and it's just not quite perfectly sealed, and the cell is not, there's a couple things that'll happen. One is then your solution is more concentrated, and you're more likely to start having precipitation of minerals. And with all the redox stuff, as we've learned, some of the redox chemistry is also related to solubility, right? So it's going to push us to a little more extremes, and then the electrodes themselves can be, you'll have potentially salt crystals and things forming on them and preventing them from working properly. I think that's related to, actually, it's probably not directly related to, but the other thing that can happen is your leads can get corroded. Now that one's a little easier fix, right? You scrape off the corrosion on the surface, it's kind of rust and whatever else. And these leads, I think they are probably also still lead, so it's probably, want to make sure you wash your hands if you do that. I actually don't remember that they might not be lead, regardless, it's pretty nasty corrosion stuff, and you wouldn't want to, like, you'd want to make sure to wash your hands, because some of that could be from the acid or who knows what. So a couple problems there, one of which you can technically do some maintenance, but it's all related to this both redox and solubility chemistry there, and acid-base chemistry with the lead-acid batteries. Okay. Any of you have any experience with any of that? Have you ever had a car battery die at least? Yeah. It's no fun when especially when it gets cold. You know, our chemistry changes a little bit. If it's going to go bad, the reactions are just less potent when it gets cold. So suddenly, as the temperature changes, that's typically when you have like, oh man, my car's not starting, or you'll find it's having trouble starting, and you're like, what's going on? Do I need to change this? Yeah. So that's some of the reasons why that may happen. Okay, so moving on a little bit, we're going to talk about this PE. I'm just going to call it. It's basically like pH, except P for the reduction potential, E. And this is essentially a measure of the free energy of electron transfer. Now, we have a small dilemma in electrochemistry in that we hear volts all the time. You know, my laptop charger has some amount of volts, your phone charger, some amount of volts. We get 110 from the wall, or maybe 240 in another country, you know, another standard. 9-volt batteries, blah, blah, blah. 12-volt car batteries, all sorts of voltage things. And in the case of a nice electrochemical cell, like the battery, maybe we can use that as a way to understand the redox chemistry. Assuming we have, as in this example, 1 molar solutions. Because that's actually also pretty nice, because if we assume there's no activity correction there, then that refers to the standard state. But that's not typically the case, and it doesn't really work out so well for every single chemical redox reaction. So in a way, it might be better to avoid using volts, because people can get confused or think you can just use a voltmeter to figure out this chemistry, which is not exactly the case. So one thing we can do is use this PE value, and we can get that just like we do with pH or something from E. So if we have this as we've talked about before, right, that combination of the units, that has units of volts. So if we take E and divide it by that, that's going to take volts over volts. So this is not the definition of E, but that was part of the definition of E. So if we simply divide it by E there, we'll get this dimensionless value. So then we can take the P of that. So we can get the standard potential, we can get the regular potential. It's just a small conversion. We don't need to worry too much about it. Just we do the math a slight bit differently and account for it. So we can also relate that to log K, because we can relate E to log K. In this case, it just simply makes it PE, the standard, is 1 over N. Again, this should be the number of electrons, I believe, that are involved with the reaction, times log K. And so we could write that PE is negative delta G formation divided by nRT times natural log of 10. That's just a conversion to get log to natural log. Or rewriting that, we can continue, rework it until we get this equation here, which is the modified Nernst equation. So PE is equal to PE standard plus 1 over N log of that activity quotient. Okay, so just saying we can get a PE value as a P form of the electrical potential, or the reduction potential. All right, now physically, I just put this block of text here because I thought it was pretty handy. So physically, we can interpret this as the measure of free energy involved with the transfer of electrons. And just like pH is a measure of the activity of H, this PE value is a measure of the relative electron activity. Now, we don't actually use concentrations of electrons, and therefore we don't do activity of electrons because we say that they don't exist free floating, right? Every time we're doing a half reaction, we have a counterbalance half reaction. We assume there are no electrons floating around and all that. Maybe if we make a plasma, but that's not what we're dealing with. So also then PE standard is that negative log of the relative electron activity of all species except E are at unit activity, or activity of 1. Okay, then it goes on to say we have a lot of relationships between how the pH works and how this PE works. And it's a little surprising there. And essentially what we realize is that just like pH is kind of a master variable for a lot of chemistry systems, on the redox side of things, PE is a similar master variable. So we've got a table that kind of compares all this sort of stuff. We can also note that, as an example, a large positive PE implies oxidizing conditions, so a low electron activity. A low negative PE implies reducing conditions, so a lot of electron activity. Okay, so we have this table. It's just going to compare the two systems, pH and PE. So we can take a general equation for the balance. How do we get H plus in a typical solution? Well, the general acid-base reaction, HA plus water gives us H3O plus. That's our H plus, right? That's like one fancy way to write H plus. When we add the H plus to a water. Plus A minus, that would be K1. On the flip side, if we take iron in a redox reaction with hydrogen, hydrogen is the real key here as the standard, like the reference point, and then iron is a typical one. I think it could be anything. They're just using it. But if pH is equal to negative log H, PE is negative log of that electron activity. So then our kind of default equation would be this half reaction, or a double half reaction with hydrogen, oxidation similar to that. We could then go and step this through to say, okay, now we have what's the interaction with an acid base? What's the interaction with a redox? So it's like acid-base system and redox system. Two equations for each of those. Thermodynamic convention when we're dealing with H, hydrogen, is 1 in both systems. Therefore, we can write up some equation that relates our rate constants essentially to get an equilibrium constant between what's happening. And we can write all of these as pH or PE systems. We also get the thermodynamics that's quite similar. We can look at what happens if we transfer 1 mole of H or 1 mole of electrons. And all of this turns out to be very, very similar. So I'm not trying to get you to memorize any one piece of this. I'm just kind of showing you how closely these two systems overlap. And if we pause and think about it, H is generally our +1 carrier as kind of the default if nothing else is going to do it. And E is going to be our -1 carrier. In some way, they serve reciprocal purposes in chemistry, especially in redox chemistry. Of course, we can have sodium or chloride doing a -1, +1 on all that. But at a fundamental level, what's going to happen in water in particular, those two are just so important, right? And so fundamental. So they're quite parallel, quite analogous. Okay, there's one other standard state that's worth considering, and that is the standard reduction potential 7, or PE standard 7. And what this is referring to is, well, our convention for standard potentials is when everything is at unity in terms of activity. So if we put H plus, well, I drew brackets, but I should put activity, right? If we put the activity of H plus equal to 1 for a standard condition, because that's how we evaluate standard things, is the activity is 1, well, that means pH is 0. And that's not very relevant to many environmental systems. Not very relevant at all. That's kind of a very limiting case. So that E naught, this standard reduction potential for anything involving H plus, we go a little stray, right? It's just maybe not as practical or directly practical. And so we could add this little 7 subscript and say, okay, well, we're doing everything like normal, except now we are putting the activity of H at pH 7. So at 1 times 10 to the minus 7. If we do that, we can convert the math and figure out the change between PE or E naught to this PE 7 or E naught 7, however you want to call it. It's just a little bit of math. It's not a big deal. That's just something that can be done, is my point, right? So that's one of the standard conventions. If we take a look at these expressions here, it's pretty straightforward. The M and N here are the number of protons on the oxidizing side and the electrons on the in the half reaction. So that's just going to give us a way to balance. Given how many protons there were, we are going to take that and protons compared to electrons, and we're applying this 7 pH 7 to that ratio, and that fixes things. So don't worry too hard about that. I mean, at this point, you're not being tested on it, right? So just learning the concept anyway. That's something that can be done and is sometimes done for practical calculations. Okay, a quick example we can take a look at to do those conversions. Basically, we can do just that. It's a manganese oxide half reaction here at the top. That's plus 8 protons and 5 electrons in equilibrium with manganese 2 plus and 4 waters. And on the bottom, we've got MnO2, 4 protons, 2 electrons going in equilibrium with Mn2 plus and 2 H2O. Okay, so got a lot of parameters, info there, and we could take a look at the solution, and we do the conversion there. Just kind of leaving it up there for your reference, in case you wanted to go through it. Okay, and we can find the 7 here, how we're accounting for the change there. And here, just do that. Okay. I don't have a whole lot to say about that, just showing that it can be done and it's not particularly difficult there. All right, what I think is a little more important and interesting are the diagrams we can make. So we've done a lot of diagrams to this point, and ultimately you probably have the feel by now. What we're going to do is find some way, if possible, to draw this by hand, and realistically we're probably going to use some computer to do it more thoroughly when it gets to the point where it's a little more complicated or we want to add something else to it, right? The same will be true here today, and my plan is to just kind of walk through stepwise where things are coming from on the diagrams. We've got 2 types of diagrams to look at. One's the PCPE, so that'll be what concentration of our species, in this case, this example, iron here, concentration versus PE. And the other one will be a PEPH diagram, which has a few other names as well. So this can be, we can derive this based on the modified Nernst equation, or if we wanted to derive it for PC versus E, we can use the regular Nernst equation. The modified is just to do the P. Okay. But this one in particular, I think we can do without solving any equations. At least that's what the book's saying. As long as we know something about the total iron and the parameters we could grab from the book's table for the two redox couples we're going to look at with iron. So we've got iron 0 valent to 2 plus, 2 plus to 3 plus. We also probably ought to know something about water, and we'll come to that as well. So this is what it'll look like, and for the next little while, we're just going to take a look at each step the book takes to draw a particular line. Okay. After that, we'll look at PEPH, doing the same thing. Just going to get as far as I can, and we're going to step through it together, so feel free to stop me if you've got questions or help me figure it out or whatever, right? So we're just going to make sense of it together. Okay, so it says, the book says, the only information we need is the Fe total and the PE standard values from the table. So we've got a couple from we've got the PE for, which one is that? It's a little hard to read. PE 32, I guess is what it's saying. Okay, that's for Fe3 plus for this reaction, and we got another one for this reaction. Okay, convention that the subscript numbers on the PE represent the oxidation states and reduced species respectively. Okay. All right, so building this, we're gonna, here are the steps. First, we take and draw the labeled axes as a fourth quadrant graph. The x-axis at the top, labeled PE. Guess we could do it at the bottom if we wanted to. And y-axis would be negative log C or PC. Okay, so we draw a graph. Then we are going to draw a horizontal line at our Fe max. So the Fe total is going to be when the x value here is 2. You could, by the way, put this as log Fe and have this as like negative 10 and so on. So you'll see plots that look like that sometimes. At any rate, we're going to take 2 and draw it across. And that's going to be kind of the max iron at any particular point we've got. Now they also have here Fe0. I guess that what they're referring to is conditions when we had a source of solid 0 valent iron sitting there, like an electrode or something. I think it'll come back to that. So anyway, I'm going to draw negative log CT at 2. Then we're going to put in system points with that equal to PE and PE equal to this standard PE at 13. So let's go up to 13 and we find this guy here. Okay, the 3,2 there, that's not 32, that's 3,2. That means, so that, I'm just making sense of this now, I apologize. The PE 3,2, that's for Fe in the 3 plus state versus Fe in the 2 plus state. That's where the 3 and the 2 are coming from. Okay, so then we should have 2, 0 here, just like that. So just for our reference, that's kind of what's going on. Okay, so that makes a little more sense. So we're going to draw a point there, and essentially this point, just like we've done in our pH diagrams, when we reach equilibrium between those two, and there's really no significant presence of any other iron species around, those two are going to be equal, meaning each of them will be half of 10 to the minus 2. On a log plot, that means we go down by about 0.3. So a small notch, about 0.3 log units lower. It's a little hard to draw that to scale on all the way down to 30 down there, but that's the point. Now, one thing we can take a note of for a moment is this is not considering any other iron species like iron hydroxides. So there's room to go more advanced than this. But just for the iron speciation itself, this is probably would be a useful starting point to say, okay, between iron without any complexation, this is what it looks like. Okay, so back to this then. So that's the first part of number 3, and then next we would want to take a spot at the PE20, and from the table we would get that value is negative 7.54, and that's going to be negative 7.54 here. Now, whereas this one is a 13, right? A 4.5, excuse me. However, they're not drawing the Fe0 valent in the same way here, but regardless, we're going to take it that 0.3 down and put our spot there. So maybe I should, move this over just a tad. Come on. Every time that happens, it's going to erase it as soon as I make another mark. Okay. Okay, so basically we're just going to do that on each of the markers where we are crossing that equilibrium spot. Okay, so then part 4, draw sloping lines that go from the system points that we just added with slopes equal to the number of electrons in change for the half reactions associated with that particular PE. So use positive slopes for oxidation forms. So +1 for Fe3+ below the 3,2 mark, and 2+ for Fe below this mark. So this slope here needs to be 2. And it's a positive 2 because there are 2 electrons going for that reaction. So in that sense, we can actually think of, in some way, the electrons changing. So per concentration change here. So how much does the concentration go up or change based on per electron moved? Something like that. Okay, and this one would be +1 slope. That was the other piece that we're saying. And what we can do is just simply draw from this point a slope of +1 leading up to it, and this one a slope of +2 leading up to it. And that lets us draw the lines. Okay. Then next should be this -1 here. Okay, and we could derive these from equations just like we've done from our pH diagrams, where we have some relationship between these two equilibria, and we have PE equals blah, 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 blah. From essentially this type of equation, right? Okay. And then it says smooth them out, and we're pretty much good. All right. I think that's just duplicating, or is that a different one? Okay. Part 5, we are going to draw horizontal lines to form the solid elemental phase, so Fe0. That's what we're going to do right here. The concentration of a solid, or the activity of a solid, we treat as 1, no matter what. So if we have solid in the situation, then that negative log of 1 is going to be 0, right? So that's kind of that situation. It's just unity. Let's see. In addition, there's no sloping line. Okay. Yeah. All right. So that's kind of the last piece. So this is just drawing up this part. Okay. Next up, we have what we would call the water reduction line. Now, what the other thing that can happen redox-wise is things can happen to water. And water itself, H2O, we can potentially oxidize or reduce. So we're going to look at the reduction first. And if you recall, when we were first balancing some redox equations, one of the things we would do sometimes is use water as an oxidizing agent or a reducing agent. Now it's a little bit difficult to do it, but if you have something that's extreme or extreme conditions, it can certainly happen. So that's the thing here. So we can take a look, and we have an equilibrium. H plus with E minus is in equilibrium with half H2. Okay, and we know the standard potential for this one is defined as 0. Sorry for the small font here. So the log K then is 0, and the number of electrons here is 1. And so we can get a PE value here. And based on that, we can write it or describe this as log of H2. So the log concentration of hydrogen H2, so the elemental form, is going to be equal to negative pH minus negative 2 pH minus PE. So for a given pH, and we have to kind of decide on one in this case for this type of diagram. So at pH 1, we then have minus 2. So this log of H2 is equal to minus 2 minus PE, 2 PE. So a minus 2 slope here, but we had to decide on a particular pH to run this at. What we'll see from the PE-pH diagrams is we'll have similar lines, but they're defined because we are crossing pH versus PE. So the decision or assumption was that pH equals 1. Let's say. So the book is making that assumption. So then we can track this with a minus 2 slope here. And we're going to do the same thing with the oxygen. Same principle, and what we end up with is a log of O2. Looks like this, where it's minus 82 plus 4 PE. So we start at a very small number, but we are growing at a pretty large pace here. So the slope on this one is plus 4. And again, the pH is at 1. We could solve this for any particular pH. So if we wanted to know what's the status at pH 7, we could solve that and plot these. The reason we might want to plot these is to say, well, under what conditions are we going to reach a spot where we start getting hydrogen gas coming off or oxygen gas coming off based on what's happening to water itself. So that doesn't sound very reasonable under normal conditions, but if you stop and think about, okay, we're doing some sort of a redox experiment, we've got some solution with iron in it, and given all that, what if we are adding a huge amount of electrical potential to it, or setting up the system where it's extraordinarily oxidizing? Something might start oxidizing water. Conversely, something might start reducing water. So if we have an electrochemical cell that has some pretty high extremes, we can start splitting water, as we call it, and forming hydrogen gas. This is actually electrolysis. That's one way to produce hydrogen gas. I think the most economical way of producing hydrogen gas is to take methane and get it from methane. Methane is CH4, a lot of hydrogens there. So conversion from methane, but the theoretically clean way, I think it takes more energy, so not as clean in that regard or efficient, is to do it to water, because you'll have products of oxygen and hydrogen. Okay, so at any rate, those are these two lines. If we give it extreme enough conditions, those will form, and maybe they'll be at relevant concentrations if we're at pretty extreme circumstances. And these are largely independent of what's happening with the iron, right? Neither of these relate to what's going on with the iron, so long as the iron's not affecting the pH, right? Okay, so one other example of a PCPE diagram, common one here is the nitrogen reduction potentials. We could look at a plot with basically everything on it. And this one's a bit simpler. I'm trying to see what the difference is. Okay, so the one on the bottom, we're excluding nitrogen gas N2 because it's usually pretty inert, so it takes some pretty extreme circumstances to get it. I mean, perhaps it's very important with Haber-Bosch process, but over here you can see nitrogen in the atmosphere or aqueous nitrogen could be relevant, and this one's just going to exclude that. And then there's some on the right over there. Okay, so we could take a look. It's the same type of principle. We could look at all the half reactions that are involved with creating this and their standard PEs for each reaction. You also see that they list them at pH 7 as well, the standard 7s. Just wanted to give you a quick glimpse of this. So if we look at the one on the bottom, a little less messy, for a lot of, I guess, redox levels, we would be in the ammonia form. Eventually we reach nitrate. The nitrite here is not particularly stable for very long. It's not usually very stable. So in a biological system or a natural system, sometimes we might have some nitrite forming. However, it's a bit slow, but it will eventually convert. So if you've ever looked at a kind of a nitrogen cycle or transformation, what might happen in a river if you discharge wastewater, or let's say if you start a new aquarium, these will occur in sequence. You'll first get a lot of ammonia, assuming you put in some brand new fish and started feeding them. They're going to excrete some ammonia. Then you're going to start getting some nitrite. That'll probably happen after the ammonia built up too much and your fish died, which is going to happen in 4 or 5 days for a brand new aquarium with no biology in there yet. So if you've ever done that as a kid or something, get a nice little goldfish and then it dies 5 days later, sad. The ammonia built up too much and it was toxic. Now, don't despair in that circumstance, because a few days later you'll have some of these nitrogen converting bacteria starting to colonize the walls, the gravel, whatever you've got in your aquarium, and you'll have a nice little biofilm that's still going to more effectively convert ammonia to nitrite. So then nitrite's also a little bit toxic, so if the ammonia didn't get it, maybe that's the thing. But once the system is rolling pretty good, you'll end up just with nitrate as your primary nitrogen species. And whenever you do add a little bit of ammonia from fish waste, it'll be converting relatively quickly, and you'll avoid the spikes, assuming you're not doing something crazy and way overfeeding them. So that's a typical example for an aquarium. Would be true for a lot of biological systems. The aquarium is an interesting one because if you start a brand new fresh one, you kind of have to find some way to prime it. Hopefully not a sacrificial fish. Maybe just add in a little bit of ammonia from household thing. Maybe use some natural rocks from a stream. Get that colony going before you tempt the fate of your fish, or at least buying any fancy ones. Okay, so all right. So that's for the PCPE ones, I think. Okay, So I think I meant to write PEPH here. Yeah, I did. So for our PEPH diagrams, these are our two master variables. So we have a few things we can look at here just by calling it that. A master variable, our pH has been our master variable for so many things this semester. We might recognize these graphs will be giving us a lot of important information or summarizing a lot of good information, right? These have also been called stability field diagrams, predominance area diagrams, EH-PH diagrams, I guess if you don't do the log, or named after, I guess, one of the first chemists who presented these, Porbet diagrams. Okay, so maybe you've heard of one or the other of those. And there's a pretty good chance that those would also be a little synonymous, or maybe people would refer to a solubility diagram or one of our PCPH diagrams in those general terms as well, right? These are all fairly closely related, a similar concept. Okay, but for these in particular, we are going to define specific areas within the lines. As we'll see, we've got lines that'll border the edges of the conditions between the PE, that redox potential, and the pH. And those borders are going to kind of distinguish what species predominates. And on the border, that's going to be where we have some sort of equilibrium between the two species, or a solubility line, or some such event. We can have three different types of lines, as we'll see in a lot of these diagrams. We'll have vertical ones, horizontal ones, or some sort of slopes. Vertical ones are going to be only dictated by acid-base, so it's only related to pH, no redox matters. Horizontal is going to be the opposite, only the redox matters, no pH, or no acid-base. And then sloping lines has a combination, right? So thinking back on different things we've studied, we can recognize some things are redox active, some things aren't necessarily going to be, at least under some circumstances. Some things relate to how much H plus is going on, and their equilibriums relate, and some things weren't involved at all with the H plus, right? So that's kind of one of those things, and of course we have some species that are going to be doing both. Okay, any diagram like this, we can also draw the water oxidation and reduction lines for it, as we'll see, defining the stability of water itself. Okay, so we're going to jump right into this iron speciation diagram, or predominance diagram. And here, one thing we'll notice is we are adding the hydroxy complexes. Just at a glance, it looks like there's a lot going on, right? So we can technically go through and stepwise, and I went ahead and copied all of the book steps to describe this diagram. So we'll see how much we can get through. But essentially, at the very basics, we're doing the same thing we've been doing. We get some thermodynamic or perhaps a governing equation relationship that's going to tell us something about the PE and the pH, and ultimately plot a line for one with the other. And each of the lines is going to be associated with some sort of equilibrium point, right? So that process, we've done it sometimes, several times already. It's more of that. It's just with a relatively complex system here. And then we have thresholds where at some point we start going with some new species. So let's just take a quick look, big picture look. So water, we have water oxidized here. So that's when we would have H2O on this side, and should be oxygen on this side, right? So we are taking from O in a 2- state and taking electrons away from it, so it's in the 0 valent state, and water reduced here where we have H2 versus H2O, right? So the protons in the +1 state, now they're reduced, given them electrons, now they are at the zero valence state. Okay, so those are the water boundaries, and these are always going to be drawn in the same manner in the same locations. So we could look up all this stuff, but one thing we can also note is that when, by definition, when H plus activity is 1, the standard potential is defined at 0. So if the standard potential is at 0, the PE, the way we do that conversion should also be 0. So when this would be the activity of H plus equals 1. Okay. So a couple things there. Then we recognize that at low pHs and kind of mid-range PE values, our soluble form is Fe2+, or Fe2+ is stable under those ranges. If we have particularly reducing conditions, we can get zero valent iron. Okay, particularly oxidizing environments, we get Fe3+. Now, a little more typically at a lot of pHs, even if we're in a 3+ state, we will be complexed with hydroxides, right? So I'm not saying that it's only in the 2+ state here, and this is the only 2+ state or area, or that this is the only 3+ area. This is iron 3+ by itself, and this would be iron 3+ with 2 OHs, right? That species begins to dominate. Okay, so that's kind of how we can look at this diagram as a whole, and this is why, you know, you might be able to start seeing why we would use them, is because we might say, okay, well, our particular water has some redox potential, and you might have, if you've done some sort of water chemistry, you might have measured this as the ORP, oxidative reduction potential, or oxidizing reduction potential. So a given water has some given species in it that may be a little bit reducing, maybe a little bit oxidizing. They can convey to the water itself some PE value, meaning that it is prone to take or give electrons in some way. So given that, we can look at what pH we have, and then we can expect to know something about which species predominates. Now that doesn't mean there's 0 Fe2+ right here. It just means that right here there's 50% Fe2+ and 50%, or rather these two are at equilibrium, so approximately 50-50, right? So these lines are not meaning completely exclusive, just you know, that's the boundary, and these are log plots, so if you go far from it, generally you're not going to have much of the other one. Okay, does that make sense? All right, we actually only have 4 minutes left, so I'm not actually going to continue through. I'll flip through a little bit just to paint the picture for you. We have a table here that could give us all of these, the constants and the reactions at play here, right? We could identify each one of those, each having an equilibrium constant for it, and the appropriate equations, and we could draw each one of those up. The table continues, it's a big table. It goes like that. Hopefully, you know, hopefully your Thanksgiving table will look at least that big. We could do the water reduction line. There's the math for that. We could do the water oxidation line. There's the math for that. We could then start drawing them piece by piece. So we've got a horizontal line here, a vertical line there, a sloping line there. I guess that wasn't quite as many. So, but point is, we can draw each piece of that and build that. Okay, the Mintech software, I think, does a lot of that. You just have to put in the right inputs. And if you were going to tackle that in MATLAB, you basically just need to kind of follow this this type of process where you're going to identify essentially this table or an equivalent of this table and say, okay, what all do I need? Where is this piece going? And let's add a segment of my matrix that's going to be these values, these XY values, right? So it's plausible. Conceptually, it's not too hard, but there's a lot of moving pieces, okay? A lot like any of the other diagrams we've drawn. All right. That's really all I've got for you, and have a fantastic Thanksgiving. That's loud.